So it's been a while since I've done a lecture for you, and I apologize for that, but I just went through a really gut-wrenching bout of midterms. Yes, I'm a student too, getting my PhD in optics actually. And now it's time to blow off some steam by getting back to what I really love, which is optics. And we're going to switch gears from what we've been talking about recently. We've Instead of talking about waves, we're going to get back to ray optics for a bit and really finish that off and round it off more completely so that you can sink your teeth into stuff and actually start designing things using your knowledge of ray optics. So let's go ahead and do what we need to get there. In ray optics, we've talked about bending light and using lenses and things of the sort to form images, but I wanted to touch on a topic that we haven't really covered at this point, which is magnification. So if we have a normal convex lens, this is a double convex lens here, both sides of the lens are convex, then we've gotten pretty accustomed to the fact that this has a focal length on both sides of the lens. So let's do a few examples with these lenses to try to get a feel for what it means to be magnification. I'm going to give a first example where we're going to make the focal length f equal to 1, just say 1 meter, the units don't really matter, and we are going to make the distance to the lens x1 equal to 2. And then we want to see what happens to the image on the other side of the lens here. So I'm going to do our trusty ray tracing, and I'm going to draw our focal ray a little badly. Then I'm going to draw our center ray, chief ray, what have you. It looks like I've done this well enough to get the point across, and I'm going to draw my parallel ray, which then gets passed through the focus, and all three lines magically converge upon each other because my artwork allows me to bend the line slightly. In this case, we actually happen to get a real image that is inverted or upside down, and if my artwork is good enough, this should be the same size as the original, which means that this is a one-to-one magnification. Technically, the magnification here is -1 because it's inverted. So let us take note first of the imaging equation that we've used a few times at this point. Here x1 is 2. We don't know x2 yet. We know that the focal length is 1/1. Well, 1/2 plus 1/2 would equal 1, so x2 in this case also equals 2. Now, this is a bit tricky. I've mentioned this before, but I want to reiterate. x1 here assumes that the object in question is to the left of the lens. So x1, let me write this out. x1 is positive for objects left of the lens. I hope I can write all this out and still have enough time to get through all of this. Let's see, and it's negative for objects right of the lens. And x2 is actually the exact opposite of this. So x2 is negative for objects left of the lens because the object is normally to the right of the lens. It's positive for things on the right of the lens. So here both x1 and x2 are positive because x1 is on the left and x2 is on the right. And we note that x1 equals x2 in this case, and they're both equal to 2. And magnification, which we'll just call m for now, is -1. So that's pretty interesting. Let's move on to a new example where I have something that usually terrifies me. Even in the lab, I don't like to do this just because it's very weird. I like using the actual focal lengths of the lens. But what I'm going to do that's so weird and scares me so much is I'm going to put an object right here, closer to the lens than the actual focal length. We're going to say, once again, that f is 1, and that x1 in this case equals 1/2. So you might say, how in the world are we supposed to solve this? When I first did this, I sort of panicked as well, because I wasn't sure that what I had taught you to do would actually work, but it turns out that it does. All you have to do is do your focal rays and chief rays, and just like you normally would. So if we have a beam coming from the focus through the object to the lens, that's your focal ray, which will come out parallel. And then if you have a beam of light coming from the object through the center of the lens, that will not change, and that ray will come through the lens undeterred. And then our final ray is our parallel ray, which comes to the focus on the other side. So we actually have 3 rays that are actually diverging on this side of the lens. So if we trace all of these rays back, oh, I hope I do this right. It's very important that I do it right, which of course means that I'll probably mess it up horribly. But if we trace these rays back, a little artistic creativity there, but you'll see that there's actually an image formed here. It's actually not a true image, it's a virtual image, because the image is formed from diverging rays and not from the actual image itself. So for another good example is if you have a diverging lens and you have an object on this side, then the light passing through will diverge, making it look like the image is actually over here somewhere. When it actually does not form a true image, we call that a virtual image. And that's what we have in this case, and in this case. But up here, we have what we call a real image. Generally, if all the rays actually do converge, then you have a real image. If they don't, then you have a virtual image. If you were to take your eye, here's a poorly drawn eye with some eyelashes and a cornea. If you were to look this way, you would see the object as if it were here. That's why we call it a virtual image. Anyway, so let's use the imaging equation once more to figure out exactly where x2 is. You might see that I've drawn it at a very convenient position, but let's go ahead and make sure that what I've done is correct. 1 over 1/2 plus some quantity equals 1 over 1, or just 1. This is 2, so if we subtract both sides by 2, then we have 1 minus 2, or minus 1, which means that x2 is equal to -1, which turns out to be exactly where I trace the rays to be. Remember, x2 is negative when it's on the left side, and in this case, x2 turned out to be negative. So now we have a situation where x1 was 1/2 and x2 was -1. So you'll see that between this example with this x1 and x2, that's a very bad x2, but hopefully you can read my handwriting. That's a 2. It's not a squiggly mark. My professor today had really bad handwriting on the blackboard, so I need to make sure not to do the same thing. Here, the quantities were equal, x1 and x2, in this example up here, and the magnification was equal, but inverted. And here, x2 was negative, and twice the amount of x1, and the magnification here is 2. It's not -2, because the virtual image is not inverted. So it's just 2. It's twice the size of the original object. So between these two examples, you can probably, I can't really fit both of them on the screen at once. Let me copy this down here for you. And if you see both of these situations, you will come up with an instance or an equation, or you can come up with an equation that just states this: that magnification is the opposite of the ratio of x2 over x1, or the distance after the lens over the distance before the lens. This satisfies both of the examples I just gave you, and it holds true for thin lens paraxial systems. It doesn't have to be a single lens. In general, let's see, I was going somewhere with this, and I better make it quick because I'm running out of time. Oh, yes. What this tells you is that there are two ways to magnify something. Let's say you have some object over here. I'm trying to decide where to put it. And we want to magnify it as much as possible over here. There are two ways you can do it. You can either shrink x1, move the object closer to the lens this way, or you can increase x2, which means that you're moving where you actually look at the object further away. You can also look at this the opposite. If you are looking at this object here and you want it to be imaged over here on your eye, then if you bring your eye closer to the lens, you will actually be able to magnify this object. And conversely, if you move the lens further away from the object, you can also magnify it. So I have some devices I've actually made in the lab, and in order for me to see them, I take the lens and put it basically right next to my eye, where my eye is pretty much at the focal length. If I get any closer, then I won't be able to focus an image because it would form a virtual image on the wrong side of the lens. So basically I cram my eye here and put the lens really far away from the object I'm trying to see to maximize this magnification. Anyway, there you have it. This is magnification with lumped systems and single lenses for ray optics.